Okay, yeah, so we're talking about dynamics of molecules at surfaces. We've been talking about energy exchange mechanisms between molecular degrees of freedom and surface degrees of freedom. Last time we talked about coupling of molecules to the phonons of the surface, and today we're going to be considering the electronic degrees of freedom of the surface. And so, like we said last time, the molecule can either couple to phonons, which are the ensemble of vibrational degrees of freedom of the surface, or they can couple to electron-hole pairs. So in other words, it's possible to promote the electronic energy of the solid so that one or more electrons are excited, leaving an unoccupied hole behind, or vice versa. You could also take energy from an excited electron and couple it to a hole, put it into a hole state. Okay. Okay, so I'm going to be focusing on conductors, so metals. And if you have a metal system, well, actually, anytime you have a solid system, to a good approximation, the properties of solids can be divided into vibrational dynamics and electronic properties. So in other words, we're going to apply the Born-Oppenheimer approximation that we've been using for molecules. Hey. Right, so this is the Born-Oppenheimer approximation, or also called the adiabatic approximation. However, with a molecule, typically we can apply the Born-Oppenheimer approximation and then do some sort of high-level electronic structure calculation involving all of the electrons. But for a bulk solid system, that's no longer the case. This is not going to be possible because we would have to, even if we hold the nuclei clamped, we would still have to solve the Schrodinger equation for, something like 10 to the 23 electrons in order to get bulk properties. And that's just not going to be feasible. So our approach is going to be, we're either going to have to use some sort of simplification, such as we can consider a small part of the solid and use a periodic boundary condition on the electronic wave function, similar to how, like we talked about previously, or we can use some sort of simplified model to consider the electronic structure. And so that's what we're going to do today. Okay, and so if you consider the electrons in a metal, then basically the potential that an electron is experiencing involves a periodic lattice, right? So, basically a cartoon of the potential would look like this black curve where at each positively charged nucleus, the potential drops down, and then between the nuclei, the potential increases, right? So you have sort of this periodic potential that varies with the atomic lattice. And then at the edge, there has to be some sort of edge effect, so the energy rises to a level called the vacuum energy, which is the energy that an electron would need to have in order to escape from the metal. But as a simplifying approximation, we can ignore these wiggles down here, and we can just treat the potential approximately like an infinite square well, as shown in a dotted line. Okay? And so then this is going to reduce the system to a simple particle in a box system, which we know how to solve. Okay? And so if we do that, then we're going to treat the particles as being in a 3D box, right? So a cubic box with side length L. Then the Schrodinger equation is going to look like this, where the potential is going to be 0 if you're inside the box, and infinity if you're outside the box. Okay, and I think that we're very well familiar with this problem, so I'm not going to take you through the solution, but just to remind you what the solution is, for each degree of freedom, x, y, and z, you get a normalization factor of square root of 2 over L, and then you get a wave function that oscillates like a sine wave. Okay, so you get sine of kx times x, ky times y, kz times z. And the eigenenergies of the states are going to be h bar squared over 2m times kx squared plus ky squared plus kz squared, or if you treat k as the vector sum of kx, ky, and kz, then you can substitute, instead of this expression in parentheses, that's just the total wave vector k squared. Okay, and so there's going to be boundary conditions because the potential goes to infinity at the edge of the box, and so the wave function has to go to 0 at the boundary, and so therefore kx, ky, and kz cannot take on any value. They can only take on discrete values, and so therefore the energy states are going to be quantized. So kx, ky, and kz have to be equal to pi over L times their respective quantum number, nx, ny, or nz, where nx, ny, and nz are positive integers greater than or equal to 1. Okay? So next what we want to know is what is the density of these electronic states in the solid. And we can take an approach similar to the approach that we used for the phonon densities of states. So here's the equation for the allowed values of k squared. If we divide this equation by k squared and rearrange it, we can get this form. And this is the equation for a sphere in the coordinate system nx, ny, and nz. And so the sphere has a radius of kl over pi, and so therefore the volume is just 4/3 pi times the radius cubed. And so if we want to know how many states there are that have a wave vector k or less, then each allowed state corresponds to 3 positive integers, nx, ny, and nz. And so therefore all of the states, all of the allowed values of ny, nz, and nx that are below some value k is given by 1 octant of the volume of a sphere, because each state basically in this picture represents a cube of volume 1. And so the total number of states equal to or below a certain wave vector k is just going to be, you're only allowed to have positive values of n, so we just take 1 octant, so 1/8 of the volume of this sphere, 4/3 pi times L cubed, k cubed over pi cubed. And so if you simplify this expression, you get this expression here, 1/6 L cubed, k cubed over pi squared. And next we're going to consider what's the number of states between k and k plus dk. And so that's going to be, some differential of the number of states, right? So it's some density d of k times some differential dk. And so this density is going to be just the derivative of z of k, right, which is the total number of states with respect to k, dk. And so if you take a derivative of this function here, of this expression here, then you get something that goes as k squared, right? Because we're taking the derivative of k cubed with respect to k. And, right, so now we have a density of states in terms of the wave vector, right? How many states per unit k? But what we really want is density of states per unit energy. So we're going to convert that to energy. So the energy, recall, was h bar squared k squared over 2m. And so the differential of energy is just going to be h bar squared k over m times dk. And if you plug these two expressions into this expression here, right, so solve this expression for k, you're going to get dE over, or dE times m over h bar squared k. So you're going to plug this in, you get a factor of k in the denominator. So you're left with 1 factor of k. Solving this expression here for k, you're going to get something that goes as the square root of energy. And so if you plug that in for the factor of k that's remaining, then you get an expression for the density of states as a function of energy. And it goes as the square root of E. Okay? And you're left with some constants. You can check that I did all the algebra correctly. Okay. Okay, so this is the total density of these particle in a box states. But so far we've been ignoring the fact that these are electrons. They can be in a spin up state or a spin down state. And as we know, based on our experience with chemistry, each spatial orbital can accept 2 electrons, right? One in the spin up state, one in the spin down state. And so the total density of states is going to be 2 times this density that we derived. So multiplying this expression by 2, we get this expression here, right? So the 4 in the denominator becomes a 2. And so notice I've substituted, instead of L cubed, I've substituted volume. But the density of states per unit volume is obtained by taking this factor here and dividing by the volume. And that's what we're going to call the density of states E. So d of E is going to be this expression here, right? So just this part divided by the volume. Okay? So we know the density of states at each energy. How are they going to be populated? So this is one way in which there's a really, really big difference between the behavior of phonons, degrees of freedom in a solid, and the behavior of electronic degrees of freedom in a solid. So not only is the density of states expression a little bit different for electronic states, but also electrons are fundamentally very different from phonons, because phonons are quasi-particles that behave like bosons. And so if you have a boson and you cool it down to a low temperature, all of the bosons can go into the same quantum state. And so as T goes to 0, all of the phonons in the solid go to the ground state. And you can have a solid that's essentially not vibrating. It only has 0-point vibration. But electrons, on the other hand, are fermions, so they cannot all go to the ground state. They obey Fermi-Dirac statistics, and you can only have 1 electron per spin orbital. That's essentially the consequence of the Pauli principle, which says that no 2 fermions can occupy identical sets of quantum numbers. And so, these are the results that we have. So you can plot the wave vector as a function of energy. You get this k squared. Energy goes as k squared. We also derived the density of states as a function of energy, right? So the function is sort of turned on its side, but the density of states grows as the square root of the energy. And basically we're going to do the same thing that we do with molecules, which is if we have a molecule, there's a certain number of discrete spin orbitals. We fill the spin orbitals with electrons, starting with the lowest energy orbital and then going up in energy until we run out of electrons, and then we have the electronic configuration in the ground state. The difference here is that we don't have discrete orbitals anymore. There's too many orbitals to treat them discretely. There's essentially almost an infinite number of orbitals if you have a bulk metal. But we know the density of states per unit volume. And so we can fill that with electrons until we run out of electrons, right? Because we know the density of electrons in the metal. And then we're going to sort of fill up these states until we get to a certain energy where we run out of electrons. That energy is called the Fermi energy. So this is the energy of the highest occupied electronic state at 0 Kelvin. Okay? Okay, so so in the lowest energy state at T equals 0, the available electrons occupy successive energy levels starting with the lowest, and the electron density per unit volume, N, that could then be expressed like this. So it would be, you integrate over the energy of the density of, how many states are at that energy, density of states at that energy, times the occupation of those energy levels at a certain temperature. Okay? And so at T equals 0, this occupation function, F, is going to be a step function. So the occupation is going to be 1 if the energy is less than the Fermi energy, and it's going to be 0 if the energy is greater than the Fermi energy. So all the orbitals below the Fermi energy are going to be occupied. All the orbitals above that energy are going to be empty. Okay? And so as an example, we can take a simple metal, such as gold, and we can calculate, just based on this simple model, what is the Fermi energy of gold. So starting with the density of gold is about 98 moles per liter. And the electronic configuration of the outer shell of a gold atom is 5d10, 6s1. And so what that ends up meaning is the d shell is full, so basically the d electrons stay bound to the gold atom, but this half-filled s shell of electrons is going to contribute to a conduction band in the gold metal. So the s electrons are just going to be free to explore these particle in a box states. They're going to be delocalized. And so that means there's 1 electron per atom that gets contributed to this valence band. And that means that n is approximately 6 times 10 to the 22 per cubic centimeter, right? So it has the density of 1 electron per gold atom.